Okay, let me go ahead and get started. So we've been dealing with transistors now for about 2 lectures, and there is something I want to bring up now, which is the transistor characteristic curve. Actually, let me adjust. I think the focus is off as usual. There we go. Okay, the default always seems to be set to auto. Okay, so the transistor characteristic curve. Okay, so what we're going to do is we're going to try to relate the voltage between the collector and the emitter, the collector current, and the base current. Those are kind of our 3 values we've been really interested in when we're analyzing any transistor circuit. And we referred to this as the operating point. Okay, so to the transistor characteristic curve, just a fancy way to describe the relationship between VCE, IC, and IB. And these 3 together we referred to as the operating point. Okay, and the way we're going to go ahead and represent this relationship, we're going to actually plot the collector current along the y-axis and VCE along the x-axis. So if I go ahead and try to draw this in here, we're going to put IC along the y-axis in milliamps, and we're going to put VCE along the x-axis in volts. Okay, and we still need to refer to the base current. Now, the way we're going to do this is we're going to keep the base current to be constant for any one of these curves. So we're going to show multiple curves along this graph. And let me go ahead and draw one right here. Okay, and let's go ahead and say VCE is about 1 volts over here, 2 volts, 3 volts, and it keeps on going until we get to our max VCE for describing our characteristic curve for a given transistor. So each transistor, even if I were to purchase 2 of the same exact transistors, might be slightly different in how their characteristics perform. And so this one curve right here, let's go ahead and say this is at about 0.5 milliamps. And this one is for a base current of 5 microamps. Okay, so I am drawing a generalized characteristic curve for a fictitious transistor to kind of demonstrate this relationship over here. And if we go ahead and increase the base current, we know that we should get more collector current, right? Think about your base current as being controlling the amount of collector current that flows through your transistor. Let me draw up a transistor here. I think visually it kind of helps to see this. Okay, and so the collector current is equal to beta times the base current. So if we increase the base current, we should get more collector current. But notice we're looking and plotting it as we increase the collector to emitter, the collector to emitter voltage goes up. So let's go ahead, let's look at another curve here. Okay, and let's say that this curve was plotted for a base current equal to 20 microamps. And now you can kind of see our beta is kind of leaning towards 100, right? For 5 microamps of base current in, we got 0.5 milliamps. For 20 microamps of base current going in, we get about 2 milliamps of collector current flowing through our device, and we can keep on plotting these curves at different base currents to define the relationship between the collector current and the collector emitter voltage. So let's do a couple more here. Okay, so now let's say we got a base current of 40 microamps and a base current of, let's say, 75 microamps. And we'll see 7.5 milliamps here and 4 milliamps here. Okay, so this is how it's done to characterize a transistor. Since we have 3 inputs, we have a separate curve for each different base current. And then if you didn't have a curve for a specific base current, like let's say 30 microamps, you can kind of interpolate between these two and see, oh, at about halfway I expect it to perform kind of like the one below it and the one above it. And so this ends up being the entire set of characteristics for a given transistor. And in fact, what's kind of neat, and this is something I've been playing around with lately, is this used to be a little more popular to look at to have a device called a curve tracer. Let me pull that up. Here's actually a good example of a specific device to do just that. And so the device under test would be a transistor, and then it plots a curve for each one of those base currents that you'd be interested in. And you can go ahead and characterize a transistor this way. Here's another image done digitally of the same thing. Now, we've been dealing with kind of an idealized transistor, but the truth is, if you notice, the collector current kind of increases a bit. So if you think about your collector current as kind of increasing for a given base current, right there, this kind of tells you that beta is not a fixed value. We would like it to be a fixed value. Beta kind of gets in the way. We would like that nice, always static relationship between the base current and the collector current, but unfortunately, real parts, real world, we're just not going to get that. Okay, and it's very evident here, especially at higher base currents, where this is quite drastic up here. I don't know what transistor they're specifically looking at, but you can see there's quite a big difference where I'm circling with my mouse over here versus over here in terms of the collector current. Each one of these lines is a constant base current. So if the line is sloped up, then we know that beta is not staying constant. However, in my drawing, I have tried to keep beta fairly constant with a straight line across. Okay, so how do we get this? How do we plot this curve? We're going to need a test circuit for any given transistor to go ahead and plot that. And what's generally done is we will have some current limiting resistor into the base of our transistor, and some current limiting resistor on the collector of the transistor. And then we're going to give ourselves some variable voltage sources, some voltage sources that we can go ahead and change. And I'll draw them like this. However, I will put a diagonal arrow through it, and anytime we put a diagonal arrow through a part, it just means it's variable, that we can actually change that. Okay, and the same thing for VCC. We would have a variable voltage over here for VCC, and VBB for our base bias voltage and our collector bias voltage. This needs to be referenced to ground, as well as this. And then, of course, we are plotting the base current, the collector current, and VCE for trying to see the relationship between all of our operating point parameters, our VCE, IC, and IB. Okay, and let's see, just for a couple of values in here, let's give ourselves a 10K, and you would put some value of resistor up here, something like 100 ohms, 200 ohms, 300 ohms, and then plot this. Okay, how do we go ahead and plot this? How do we get that characteristic curve? Well, if you are working with a part and you go ahead and open up the data sheet for that specific part, you're going to, in some image, they're going to show this, because this does kind of define the transistor as a whole. Okay, they'll give you many other drawings in the data sheet, but this one would be one of the primary ones that you would want to look at, and we'll see why in a minute. Some of the details that we can extract that are useful from this characteristic curve, and also another piece of analysis, another tool that we can go ahead and use to understand how a transistor operates in our circuit. So let's just quickly go over kind of the procedure to generate this characteristic curve. So the first thing we actually want to do, since we are drawing a curve for a specific base current, is we want to set the base current to be a static constant value, okay? So we want to pick a VBB that gives us a specific base current, so that we always have, say, something like 5 microamps or 20 microamps running into our transistor of base current. So let's go ahead and let's say for step 1, what we're going to do is pick IB for let's say for one curve. And how do we pick that? Well, of course, the base current is equal to whatever VBB is minus the voltage drop between the base and the emitter, and divide that by the resistance gives us that base current. So IB is equal to VBB minus 0.7 volts divided by, in our case, we had a 10K limiting resistor, current limiting resistor connected to the base. So this goes ahead and relates VBB to IB. So if we wanted, for one curve, let's say, for example, we wanted this to be 40 microamps, then we would go ahead and just set up the equation such that 40 microamps is equal to VBB minus 0.7 volts divided by 10K. And therefore, if you solve this, VBB will be equal to 1.1 volts. So we go ahead and we adjust our power supply to set this at 1.1 volts. And then we're going to start playing with VCC. So step 2, start with VCC at 0 volts and increase while plotting IC and VCE. So you can kind of think of your IB as being that input, and then we're interested in what IC and VCE does at a fixed base current. And so these two steps right here with this circuit is going to produce one curve on our characteristic curve. And then we go ahead and repeat this over and over again.
Wait, Professor?
Yeah.
Where does the 0.7 voltage or voltage drop come from?
Yeah, it comes from inside the transistor, the PN junction between the base and the emitter.
Is that standard for all like transistors, or is it different for all of them?
All silicon-based transistors, we're going to treat those as having a constant 0.7 volts just because of the nature of their construction. So if you look inside of this transistor, you have that NPN sandwich. And so if you just look at the base circuit over here, you have a 0.7 volt drop, which is that, from the semiconductor physics perspective, that's that barrier voltage that you need to exceed in order to get any current to actually start flowing from our base to the emitter.
Okay, gotcha.
Yeah, cool.
Is it different for PNP ones?
No. Where it's different is if instead of a silicon-based diode, we were dealing with a germanium diode. And in fact, the first transistors that were constructed with germanium. Germanium's just easier to work with from a physics point of view. So when they first started working on transistors in the late 40s, early 50s, it was much easier to purify the germanium and then grow the germanium crystals and then add the dopants in there in order to create our transistor. But silicon ends up working, I don't want to say better than germanium, but you get the added benefit that you can actually create large circuits with silicon than you can with germanium. So if you're just making one transistor and you're starting off in the 50s, germanium makes a lot of sense. But if you are trying to actually create, millions of transistors on one piece of silicon, then silicon ends up being much easier to work with, just because silicon allows you to grow an oxide layer, and that oxide layer ends up being really useful for the construction of integrated circuits. But yeah, that's getting off into That's headed off into the weeds if we keep talking about that. Okay, so we want to go ahead and once we've plotted one curve, we go ahead and change IB for a different one of these curves, and we do the same thing, set VCE at 0, or VCC at 0, and then increase that while we plot VCE and IC, and then put those on here. So that's how they actually characterize the transistors. Now, one of the things you've probably noticed, as much as we would like this to be an exact science, every part does kind of come out of the oven a little different. Just the nature of creating these components, you do get slight variations. So what they typically do is they shoot for a certain set of properties from a transistor. Maybe I want a transistor more so for controlling power, or maybe I want a transistor that's better for amplifiers, or maybe I want a transistor that behaves like a better switch for a switching application. And so that's why you get thousands and thousands and thousands of different types of transistors, and they evolve over time and they get better. And so what they typically do is you try to design for a transistor that gives you a certain desired set of characteristics. You construct the thing, and then you go ahead and you profile its characteristic, and then you can sort of compare it to other ones. You come up with a transistor that you're going to sell to market, and then in the data sheet you actually publish the real characteristics that you extracted from the device after you made it. Provided that it fit what it was that you were trying to bring to market. So, characterizing these things is an important aspect of working with them, I guess, is my point with all of that. Okay, so now let's go ahead and let's kind of look at this and sort of extract some useful, meaningful information from this. The first thing that we want to notice is that this first curve kind of defines the base current that we get flowing through the circuit. If we are below, then we have no current going in. And if we have no current going in, then this transistor is behaving as though it is open, right? It's within its cutoff mode. So we generally define along the x-axis at the bottom as being our cutoff region. Okay, now I've been saying cutoff mode a lot, but now that I think visually we can see these relationships, it makes sense to talk about the cutoff region, the whole area of operation at which this transistor behaves as though it's an open switch or in its cutoff mode. We define that as its cutoff region. Okay, the other extreme that you can get from here is where our transistor is within its saturation region. So you are giving it enough base current such that it is no longer limiting the collector current through the device. It's behaving as closed of a switch as possible. Now this actually occurs in this whole area here along the y-axis. This would be the saturation region. And then on top of that, we have everything that's happening in between the saturation region and the cutoff region. That's our linear mode of operation. This is where the transistor behaves as though it's limiting the current flowing from the collector to the emitter. And let's see. What did I want to say about that? Where beta matters, right? Where that inherent gain of our transistor. And so this whole area is our linear region. Okay, so on this characteristic curve, we can see our cutoff region, our saturation, and our linear mode of operation, our linear region. So everywhere in between here where the transistor is operating, we get that relationship of beta between IB and IC. Okay, now I want to go ahead and use this characteristic curve in order to do another type of analysis on our transistor circuit. For any given transistor in a circuit, we can define its operating region. Now, for a transistor that's not actually plugged into a circuit, you can go ahead and look at all of its characteristics. But once we go ahead and actually attach some values, so if we attach some values over here, now all of a sudden we no longer have all possible operations of this transistor. We're actually now going to be fixed to what ends up being a straight line across this characteristic curve. Now we're going to go ahead and this is known as the load line analysis. Okay, now what we're going to do for load line analysis is we are going to find out for a circuit where does cutoff happen, and we're going to find out where saturation happens. If we can find where saturation happens and where cutoff happens, we can actually draw a line through that characteristic curve that defines all operating points for our transistor in an actual circuit. So let's go ahead and let's say cutoff happens at VBB equal to 0. If VBB is equal to 0, then IB should be equal to 0, because obviously we haven't exceeded that forward voltage drop inherent in the construction of our transistor. Therefore, we get no current entering our transistor. So cutoff occurs at VBB equals 0, IB equals 0, therefore IC equals 0. However, if I have 0 current entering my transistor, what should VCE be for this circuit? What is VCE equal to? Think about that for a second.
12.
Yeah, 12, right? Yes, if cutoff occurs at VBB equals 0, and we're at 0 and we have no current flowing in, this transistor should be operating within its cutoff. If it's operating within its cutoff mode, then we have an open circuit between here and here. We get no current flowing through the 1K, so we get no voltage drop across here, and we measure or feel or sense the full voltage being applied here, even though no work is being done. So VCE is equal to 12.
Professor,
This-
I don't know if it's just me, but I think your mic is popping a little.
Is it? Okay, so continuing on. So we know cutoff is going to occur here, and VCE is going to be at 12 volts when we're in cutoff. Now let's go ahead and define that upper bound at saturation. Now, saturation occurs, well, when we have saturation, we look at the saturation model, and the saturation model says we get a 0.7 volt there. And 0.2 volts between the collector and the emitter. And if we're talking about saturation, what our transistor's doing, yes, this is true. We would take it to be 0.2. However, for the sake of doing the load line analysis, we're going to one-up this 0.2 volts. We're going to be as saturated as we possibly could ever be. In other words, we want to look at the behavior of our transistor in the circuit as being as close to 0 as possible. That means if we are a real switch, we're going to be at 0 volts between the collector and the emitter. So we're going to take VCE to be 0 volts. And now we want to know what IC is equal to when we have a 0 volt drop between our collector and the emitter. So if I have 0 volts across here, then this entire 12 volts is being dropped across this 1K. So the amount of current that's flowing from the collector to emitter is no longer governed by the transistor. It's only being limited by this resistor up here, the collector resistor. So if we want to know what IC is equal to at saturation for the sake of doing our load line analysis, then we will take 12 volts and divide it by 1K. Okay, so now we have a lower bound and we have an upper bound where cutoff occurs, where saturation occurs. Now we can go ahead and look at this on our characteristic curve. So again, IC here, VCE here, and cutoff occurs at 12 volts. right here along the x-axis, along the VCE axis at 12 volts with 0 current flowing through it. And the same thing for our saturation. Saturation is going to occur over here with 12 milliamps of IC.
So for saturation mode, is all the power being dissipated in that resistor above the emitter transistor?
Yeah, that's the nice thing about having a better transistor with a lower saturation voltage, is that I can dissipate more power because I have less voltage drop across the terminals, right? If you think about it, 0.2 volts, another word for having a switch that has 0.2 volts across it is a shitty switch, right? Because a switch should have 0 volts across it. But in our case, if our transistor is acting as within saturation mode and it has a 0.2 volt drop across it, it's a bad switch. But it's still a switch, and it's a useful switch. It's just not a very good one. But yeah, if I had 0 here, I'd have no power dissipation. I could put as much current through that thing as I want. But even your best transistors, even your best MOSFET, which would be ideal for that specific type of application, with a 0.001 ohms between the top and the bottom, even that is going to dissipate a good amount of power when you have large current going through it. Okay, so now we can draw a line from our collector, from our saturation. Let's write that in here. Saturation and cutoff. And we now know for this transistor in this circuit, the only place that it can operate on is somewhere along this line. It's either going to go full saturation, full cutoff, or it's going to be within the line, which would be its linear mode. So now we've taken all possible points of operation for our transistor, and we've found for our specific circuit, it could only operate along this line. Okay, so that's kind of what the goal of load line analysis is to see all points of operation for a transistor in a specific circuit. So that's what we got here. Okay. However, this was looking at it for all changing base currents. So if you think about this as an input, so if you think of VBB as your input or IB as your input, and you think about over here VCE as being your output, which that's how we're going to construct our first amplifier circuit, is by treating this point VCE, which is the voltage across the collector and emitter, as our output, and we're going to give it different inputs. If you want to amplify, say, a sine wave, your sine wave as it's fed into this circuit is going to produce different VCEs. So this changing input is what we've essentially plotted along our characteristic curve, or our IV curve. Okay, and we've defined saturation, cutoff, and our entire linear region. However, once we have a fixed voltage here, once we have a fixed voltage here, we are going to be stuck at one point along this load line. Wherever that point is that we're currently operating at, and that we would call our quiescent point. Our quiescent point is just what specific IC and VCE we are at when we have a fixed base current going in. Okay, so let's go ahead and let's kind of put all this together with our DC analysis. And let's take a circuit from scratch and solve everything. Okay, we're going to take $12 volts. 400K. $2K. And say beta is equal to 50. Okay, so I did forget to record that last 15 minutes. So what I'm going to do is just run through while I have the notes here and overview what we just did over the last 15 minutes for the sake of completeness over here. So we're going to go ahead and solve for everything we want to do about this circuit, the 400K, 2K transistor with a beta equal to 50, 12 volts applied. And we want to find the operating mode, the load line and Q point, and the power dissipated. So let me run through that. Okay, so operating mode, we're going to run through that whole DC analysis procedure. We're going to find IB. IB is equal to 12 volts minus the 0.7 volt drop from the base to the emitter, and divide that by 400. So we're finding the voltage drop across the base resistor divided by 400, and we get 28.25 microamps. It's not zero, so we're definitely not in cutoff. Okay, now to find out if we're in linear saturation, we're going to have to find what VCE is equal to. To find VCE, we want to find IC first. Now, IC in the linear model, which is what we first assumed it to be in, we went ahead and found that IC is equal to beta, which is 50 as given by the problem, times the base current that we found in the previous part, 28.25 microamps. Multiply those two together and you get 1.413 milliamps of collector current. Now we can go ahead and use the collector current to find our voltage drop between the collector and the emitter. So if we have 1.413 milliamps flowing through this, we can take 12 volts minus the voltage drop across the 2K. The voltage drop across the 2K by Ohm's law is the collector current times the resistance. So over here I'm doing 12 volts minus our 2K times 1.413 milliamps of collector current going through it. And so once you solve this out, we get 9.175 volts. 9.175 volts is our voltage drop between the collector and the emitter. Excuse me. Okay. So now that we have our voltage between the collector and emitter, it is greater than 0.2 volts. So our initial assumption of linear mode was correct. Okay, so now we essentially have our Q point where we are currently operating at. But what we want to do is find the load line. Now the load line, we are looking at the collector current compared to the voltage between the collector and the emitter, and we want to define all possible operating modes or operating conditions of our transistor for this given circuit. So it's almost like we're going to imagine that we have a changing input and we want to find the extremes that this transistor could be operating at. Well, those are going to be the cutoff and the saturation. So with cutoff, if you imagine that we have the cutoff model plugged in here, we have an open between the collector and the emitter. So we have no current flowing through it. That means no voltage drop across the 2K. So if you were to measure the voltage between the collector and the emitter, when this is open, you're going to get the entire voltage being applied. We don't have any work being done, but we do have a potential to do work. And so we measure 12 volts. And so that's where we get the 12 volts at cutoff. At saturation, we're going to go ahead and imagine that this transistor is as saturated as possible, meaning that we have a 0 volt drop between the collector and the emitter. So the only thing limiting the current between the 12 volts and ground is going to be this 2K that's over here. So if we take 12 volts and divide that by 2K, we get the full amount of current that we could possibly get in this circuit through the transistor. So 12 volts divided by 2K gives us 6 milliamps. So over here, I have gone ahead and drew a dot along the VCE axis, and we know that cutoff is along the bottom here. However, for our specific circuit, cutoff, we would get 12 volts for VCE. So hence why I've drawn it here. Now, for saturation, saturation occurs along our x-axis. That's our saturation region. But specifically for our circuit, we get an IC equal to 6 milliamps. Hence, I've gone ahead and drawn in a dot over here, marked that as 6 milliamps. Now we draw a line from saturation to cutoff, and that line goes through the entire linear region. So again, if you were to imagine that we have a changing input, not just a constant 12 volts attached to this 400K, but if we were to disconnect this circuit here and apply a changing input into this circuit, then you can imagine that our operating point, our Q point, would actually be sliding up and down this load line. So our load line defines all possible modes of operation for our transistor in our given circuit. But specifically, because this 400K was tied up to 12 volts, we already know what our Q point is. Our Q point, or our quiescent point, is currently operating at 1.413 milliamps of collector current with a 9.175 volt drop between the collector and the emitter. So our Q point on this load line should be 9.175 volts. And if you go ahead and look across at the projection on the y-axis, that's 1.413 milliamps of collector current, which kind of makes sense. 6 milliamps, 0 milliamps, this should be 3. Well, we should be halfway between 0 and 3, so 1.413 makes sense to me. So that's how we go ahead and perform the load line analysis. Now, the last thing that we probably should care about is how much power is dissipated by our bipolar junction transistor, because when you're using a real part, you can't exceed a certain maximum power dissipation without burning out your transistor. So this is good to know how to calculate. So our power dissipated by the bipolar junction transistor, well, it's going to be a combination of two things. We have a term referring to the power from our being dissipated from the base to emitter junction, as well as the power being dissipated from our collector to emitter junction over here. So if we go ahead and look at this, we have power being dissipated from the current and voltage flowing from the base to emitter, as well as the power being dissipated from our voltage drop from the collector to emitter and the current IC flowing through that. So to calculate that, we just do 28.25 microamps, our base current, times the voltage drop between the base and emitter, which is 0.7 volts, and we add to that the power being dissipated by the collector current or collector emitter junction side, and we get 1.413 milliamps of collector current times our voltage drop of the collector and emitter, which was 9.175. So calculate all of this out and you'll find we dissipate 13 milliwatts in this instance when we have 1.413 milliamps of collector current and 9.175 volts between the collector and emitter. Okay, so 13 milliwatts. Okay, so sorry again for forgetting to record that, but I've gone over it. All right, take care, everyone, and I'll see you guys next time.